what all functions you have explored in NetworkX and what all you have done using NetworkX. You can type in the chat window. Anyone? So it will help if we keep the session interactive. It will help me actually.
Yes, Suhail from Women's Politics.
Okay. Can you tell me the exact functions you have explored in NetworkX? So as ma'am said that you have created some basic graphs there. Have you tried creating some synthetic networks like random graphs or loading some data sets? Okay, Navita ma'am tells me. So you created a graph, a directed graph. Okay.
अच्छा ठीक हाँ हाँ अच्छा ठीक
Okay, so I think I get going. So what we should do is just give me a minute. I'll share my screen with you. I hope my screen is visible to you. Sorry, I'm suffering from a bit of cold. So why we are exploring this iGraph library when we already have a library NetworkX for exploring the graph is that so NetworkX is easy to command. Its commands are simple and you can work with it for smaller graphs. But when we do projects in social network analysis or whenever you handle real world data, the data is very massive and the graphs are very big. So if you have, I'll show you some online network data sets after some time. So if you look at these network data sets, they have a million of nodes, billions of edges. So it becomes very difficult to work on these graphs with something like Jeffy or NetworkX. So here is a small comparison of NetworkX with iGraph. This comparison has been done on this network here, PGP Web of Trust network. It's a directed network having around 40,000 vertices and 301,000 edges. And here you can see that their performance have been measured for some well-known algorithms. I hope you know all of these. So single source, shortest path, global clustering, you might not know about it. We'll talk about it. PageRank, a method which is used for ranking pages in Google, but you can apply it to any directed or undirected graph. K-core is used to identify the influential nodes in a network, then a minimum spanning tree and determining betweenness. So here you can see the time it takes for all of these algorithms if you use iGraph and if you use NetworkX. So we can see here that iGraph significantly outruns NetworkX in terms of time. So not just in terms of time, it also helps in terms of memory. So if you would have tried to plot a graph in NetworkX, so even if you take a simple graph of, let's say, Facebook, which is of 4,000 nodes and few, I think 73,000 edges, it will take around 5 minutes to appear in your system. And I think it's more than that. It has been a long time I worked in NetworkX, so I don't remember exactly, but on iGraph, you will see that visualization quickly. Further, storing these graphs in iGraph is easy. So iGraph, it stores your graph in using certain indices. So I'll show you when you import a graph in iGraph, it does some implicit indexing of the vertices. So it offers you a better storage of graphs as compared to NetworkX. Furthermore, it is faster than NetworkX because the functions of NetworkX, they are written in pure Python. But if you look at the interface of iGraph, its basic functionality is in C and C++, which are definitely faster. And then it provides you Python APIs to work on those graphs. So what I recommend you, I hope all of you have Jupyter Notebook installed. So it will help if you can actually keep two systems side by side so that you can actually type and see the output along with me. So take 5 minutes here and install this Python iGraph on your system. You can install it from your Anaconda terminal with the help of this command here, conda install Python iGraph. And if you are not working with Jupyter, you are directly writing Python files or using IPython, then you can use a pip install Python iGraph. Once you are done with this, go to your Jupyter window and type these commands here to check that your iGraph has been successfully installed. So once you are through these two steps, please type a +1 in the chat window so that I know that I can continue.
Yeah, Yati madam, is this Python keyword essential or pip install iGraph will also install the same on Anaconda prompt?
Ma'am, I think it is essential. It will throw an error if you just type iGraph and do not proceed it with Python.
Okay, ma'am. It has installed on my system without Python. I simply typed pip install iGraph. So I don't know why. So why?
Okay, that's good. Can you please check its version and see it
Yeah,
works?
sure, ma'am. It's 0.1.11.
Okay, okay. I'll wait for a few more minutes for everyone to install and then we'll continue. Okay, I think I should start now. I hope you are able to see my Jupyter notebook here. So our very first command is to import this package igraph as IG. So I'm starting here with the creation of a graph. So I'm going to create an empty graph here. So the command for creating the empty graph is simple graph function ig.graph, and in this function you have an attribute which is called directed. So if you set it to be true, the graph which is created is directed. I think by default it is directed, and you can set it false in case you want an undirected graph. So once you have created a graph here, we can actually go and see the summary of this graph here. You can use a summary G or you can use a print G. So if you simply type G and press enter, it will show you that you have a graph object with its memory location. If you want to see what exactly this graph is, so you see here certain symbols. So it's an I graph. The very first symbol here, D, it means that your graph is directed. So over time, we'll see these three symbols also. So right now, we don't have any of these three symbols. So these symbols are actually, there can be a D and WB. So these are the four things which can appear here. So if you see a D here, it means that your graph is directed. If you see an N here, which is right now not there, so N means that your vertices in the graph, they are named. So we'll understand what do we mean by named vertices in a while. Then if you see a W here at the place of the third dash, that means that your graph is weighted. And if you see here a B in the last dash, it means that your graph is bipartite. So in iGraph, in every bipartite graph, you have an attribute which is called type associated with every vertex. So either it will have a type of true or a type of false to distinguish between the two different kinds of nodes you have in your graph. We can use a print G or you can also use a print summary G or simply summary G here. You can also use the summary G here. So we'll show you essentially the same things. Next, I'm going to add 5 vertices to this graph. So there is one thing which is different in iGraph as compared to Network X. In your Network X, your node IDs or node index can be anything. They can be integers, not necessarily consecutive integers. They can be strings. But in iGraph, when you create the vertices, their index are by default consecutive numbers starting from 0. So what I'm going to do here is I'm going to add vertices to this graph, and this 5 here indicates the number of vertices I want to add. So this adds 5 vertices to the graph. If I again go and see the summary of the graph here, so you can see that I have this 5 here, which tells me the number of vertices. Before adding the edges, what I'm going to show you here is how do you add attributes to these vertices. In Network X, you can add using, I think, g.node and in square braces something, and then you can add the attributes. In the case of iGraph, we have two special objects associated with a graph object. So one is a vertex sequence and other is an edge sequence. You type g.vs and press enter, it gives you a vertex sequence object. So this vertex sequence object actually has all of your vertices stored here. So there are few ways to look at it. The first way to look at it is you can type a list g.vs. So it shows you all those 5 vertex objects. So these 0, 1, 2, 3, 4 here are the indices of these vertices. If you specifically want to see the indices of these vertices, you can use an iterator here. So I can type v.index for v in g.vs. So it will iterate over this object, vertex sequence object, and print index for every vertex. So you get a list here which shows you the index for every single vertex. What I want to now do is associate an attribute with each of these vertices, and let's say we want to associate an attribute which is first name. So what I'm going to do is simply g dot vh, and in square braces and in quotes I can type the attribute name here. So f name is the attribute name followed by a list which consists of 5 names because I have 5 vertices. I'm randomly going to give some 5 names here. You can use names of your own. So I have given it 5 names here and then I execute this block. So these are the f names which are allocated to all of these vertices here. And let's see if I again look at the summary of this graph here. So you can see now I have a new attribute here, f name z. So whenever you print the summary of a graph, there are a lot of things which will pop up from time to time. So first one is whether this graph is directed, weighted or not, number of nodes, number of edges. In case you have certain attributes associated with vertices and edges, you are going to see them also in the vertex summary. Okay. What next if I want to extract these attributes? So if you want to look at the values of all the attributes of all the vertices, I can simply type a g dot vs f name. So I get the f names for all the 5 vertices. If you want the f name only for a particular vertex, so you can type the index of that vertex here. So let's say I make it 2 here. So the second vertex has an attribute f name of Nihal. So the indices start from 0. 0 is for Ritu, 1 is Aman and 2 is Nihal here. Next, what if let's say I want to change a name here, or I want to select a vertex having a particular first name. So this is a small graph here. I know that this node having index 2 is having the name Nihal, but what if it's a graph having a million nodes and I want to figure out which node has the name Nihal? So for that, we have a select function associated with vertex sequence. So I can type g dot vs dot select, and I want to select that vertex which has the f name Nihal. And if you execute it, the result you see here is a vertex sequence. So it is not necessary that only one node has an f name of Nihal. It is so possible that there are 10 nodes having the f name Nihal. So what this select function will do, it will return me a vertex sequence again comprising all those vertex objects which have this f name as Nihal. And again, if I want to see which are the vertices or what are the vertex indices of these vertices, I can again fit an iterator here. So I can again do a v dot index for v in this. So if you do a v dot index for v in g dot vs, it will display you all the vertices. And but now I am doing v dot index for v in these selected vertices. And so it's going to return you a list of all those vertices. So currently I have only one vertex with the f name Nihal. So there is only one vertex in my list here. And for the sake of ease, you can even remove this dot select from here. Even then it will work perfect. So you can also write this shorthand notation like this. What if I want to delete a vertex from this graph? So to delete a vertex, we have the function here g dot delete underscore vertices, and what this function expects here is the indices of those vertices. So the list of indices of those vertices. So assume that I want to delete all those vertices having the f name of Nihal. So I can actually pass this entire list here in these delete underscore vertices and just execute this. And now look at the summary of your graph. So you now have only 4 vertices here. One vertex with the name of this Nihal has been removed. Now if I look at these indices of my vertices, so what you will see is my indices have been relabeled. So previously what was happening, this guy Nihal, he was having an index of 2. Vishal was having an index of 3 and Solanki was having an index of 4. But as soon as I remove Nihal, what happens? The indices gets renumbered. So if you look at these indices in any iGraph object, they are always going to be consecutive numbers starting from 0. So this can create a trouble sometimes when you import data sets, online data sets where your indices do not start from 0 or the indices are not consecutive. But iGraph has a workaround for that also, which we'll discuss soon. Next is about adding the edges. So I can again add a few more vertices to this graph. I'm going to add 5 more vertices to this graph now. So I have around 9 vertices in this graph, and I can again give them some names here. So right now, 4 of my vertices, they have that F name, but the others do not. So if I look at this G dot VS F name here, so it is showing me 4 names for the previous F names. For the 5 vertices which I have recently added, there are no names. So I can go ahead and add names for these vertices as well. Let me simply use some names as ABCD here. Next, I'm going to add some edges to this graph. Again, you can add the edges label wise, or so this syntax I think is quite similar to what is there in network X. So you write all the tuples in this list here. So all the edges which you want here. So if you want to add edges according to the node index, you can simply go ahead and type 0, 1. If you want to add the edges based on the names, then you'll have to do a slight workaround here, obtain a vertex sequence for that and extract it from there. So right now I'm going to add it according to the directly according to the indices. Let me add a few more here. I want to leave any one vertex isolated, so let me make it from 2 to 1. I have added these edges to my graph. If you want to look at these edges, so you can use this edge list function here. Doesn't work. Yeah. So you use d dot get edge underscore edge list to look at what are the edges in your network. So this is a very simple network generation here. If you want to see this network, visualize it. So you can use an IG dot plot G. So it shows you this network here. So currently it doesn't show you any labels here. If you want to see the vertex labels here, so in labels you can get the indices, or in labels you can also get their F names. So let's try to have these F names in the labels. So this visualization is again similar to how you do it for network X. Vertex underscore label equal to I need to provide a list which is containing the F names of all these vertices. So I saw that we can get this list using this. So you do this and then you'll be able to see the labels for these nodes here. So the things actually I forgot to talk about this. The things we'll be discussing in this session is, so we have done this. This is the first one here, creating the graphs with vertex and edge attributes. These are the other things which we are going to do. So we are going to look at various graph generators. I'm going to talk about them. Then graph representations. How do you represent them in memory? How do you store and load these graphs? Then some other graph formats. And sometimes we can use pandas data frames to read these graphs. So here we got this graph. So sometimes you just simply don't want to look at this graph. You want to store it in your system. So that process is also again very simple. You can collect this plot in a variable and then you can save it. So if you execute these two commands here, this plot will be saved in your system. I've just executed it, so you don't see it here. It is stored somewhere on my system. So mm, it's stored over here. So for Windows, it will be in your home folder. You can see this graph here. So right now this graph doesn't look very appealing. We'll make changes to it. We'll see how we can increase these vertex size, increase the edge weights, and play around with these labels and their colors in a while. Next, what we are going to look at is generating few graphs. So here we have created a graph on our own. There are few more methods to create a graph. So for that, you can actually go to this tutorial of Python iGraph. I'll also share the link with you in the chat window. So here are many different ways to generate your graphs. So you can create a copy of an already existing graph, or you can pass the vertices and edges in the same place. So along with vertices, I can also give some edges here in this fashion. Instead of assigning the edge attributes and vertex attributes afterwards, I can assign them here itself as a list. So this one over here is the attribute name followed by so this is an edge attribute. So this one comes in the form of a dictionary here if you look at it. So what it is doing is edge attributes equals to, so edge attributes is a dictionary here. This is the key here. So the keys here are the names of those attributes. So the first attribute of my edge is weight. It allocates the two edges, these two weights. You can go around with a comma here and then allocate it other attributes as well. So the key to this dictionary is your attribute name and the values is a list which consists of the values of those attributes. Then you can create these graphs from matrices. We are going to talk about it in a while in graph representations. So you can directly pass an adjacency matrix here and create a graph from here, or pass an incidence matrix. So don't worry about this. You can do it from a file. We are going to talk about that. This one is an interesting concept here. So you might have a graph which you have made in NetworkX and you want to open the same graph in iGraph now. So one way to do that is you first store that NetworkX graph as a file and then load it from there. So iGraph actually provides you a function by which you can directly convert a graph which is in NetworkX format to a format which is used in iGraph. Then we'll also talk about this in a while. How do you create these graphs from pandas, data frames, or from a formula, so on and so forth. Moving to the next part. Just a second, just give me a second here. So before going to graph representations, let's talk about a few more graph generators here. There are two types of generators which iGraph offers you. So as you can see here, there are two types of generators you get. So first are the deterministic graph generators and second are the randomized graph generators. Can anyone guess what's the difference between the two? Why one is deterministic and other is randomized? Does the name tell you something? You can type in the chat window also. The difference between these two is if you look at these deterministic graph generators. So whenever you generate a graph using this, you are going to get the same graph every time. If I type that statement 5 times, I'll get the same graph each of those 5 times. As opposed to this, in the randomized graph generator, the graph might change. The first time when I execute it, I'll get some other graph. Second time, I'll get some other graph, so on and so forth. So right away, I'll talk about deterministic graph generators. These stochastic or randomized graph generators, they use certain random functions to create the graphs. So we'll also talk about that in a while. So let's start with a few deterministic graph generators. So they help you creating some well-organized graphs. So some graphs which you see in your first class course in graph theory, graph like a complete graph or a complete bipartite graph, a tree graph, so on and so forth. So let's actually create some of these graphs and see here. So I'm going to show you some 3 or 4 uh, deterministic graph generators. You can explore more here in the manual. You can go through the manual and explore more functions here. So I'm going to show you 4 of these here. So first is a tree graph. So the arguments here are, first is the number of nodes and second is the number of children every node should have. So what will happen here? So the root node will have 2 children and after that every single node will again have 2 children and likewise. So except for the leaf nodes. So your root node will have a degree of 2. Other than that, all the internal nodes will have a degree of 3. So one comes from their parent and 2 goes to their children and your leaf nodes each will have a degree of 1. I'll also plot this here. Can actually use a box parameter here if I want to keep this graph small. Otherwise, it will take my full screen here. Let me reduce it slightly. So you see this tree graph over here. So this is the root vertex here. It has 2 children. And other than these 2 children, if you look at any other node in this graph, they are going to have a degree of 3, one coming from their parent and the other going to their children. And if you look at the leaf vertices, each of them will be having a degree of 1. We can also change the layouts of these graphs, which I'll talk more about in the graph visualization section. So as of now, we are just talking about creating a few graphs. So if you want to create a complete graph, so you can use a function graph generator full here. So this graph became very big here. Let me just reduce the number of nodes. So it's a complete graph here on 10 nodes. We can see here the graph which is generated is a directed one. You can actually remove this parameter and it becomes an undirected one. You see a complete graph on 10 nodes here. Similarly, you can go ahead and create a cycle using this generator ring. So you see a ring graph here. So other than that, it also provides you some famous networks. Like you might have heard about this Peterson graph in graph theory, which is used for proving a large number of theorems in graph theory. We should think about whether Peterson graph is an Euler graph or not and how it is used in various other theorems. So we have a number of graphs like that, Peterson graph, Robertson graph, on the name of scientists. So if you want to create any such kind of graph, so it has a graph generator, goes by the name of famous, and inside this famous, you can type the name of the graph. So let's say I want this Peterson graph here. This is how a Peterson graph looks like. So Now you might want to play here with the vertex attributes. So doesn't so it's actually a Peterson graph. So rather what I will say is I'll show you how a Peterson graph looks like. So this is what is a Peterson graph actually. So if you here look at the layout of this graph, doesn't look exactly the same, but I can say that this graph is definitely isomorphic to that one. So you can actually print the edges of this graph here to verify that. There is one more famous graph, Robertson graph, and type it and it will show you so on and so forth. Let me try one more if that comes up here. So this one is again a very famous graph. So Peterson graph and Robertson graph, they are famous if you look from the perspective of graph theory because they are used to prove a number of theorems. If you look at this Jackery graph, it's actually Jackery Karate Club Network. You might have heard of it if you are working in network. So Jackery Karate Club Network is a small network. I think it has around 23 nodes. Let's just look at the number of nodes here. I can simply look at the length of this generator here. So it has actually 34 nodes it has. Uh, so this is a network is of a karate club network. It has 34 nodes, quite a small graph. So it is used in a large number of so it is actually used as a test graph in most of your network algorithms. So if someone is going out doing a community detection algorithm, they will use it as a baseline for many other algorithms as well. So that's why they have provided a direct function here to create such a Jacari Karate Club network. Next, moving to how do you represent these graphs in your memory? If I want to store such a graph or load such a graph from the memory, so assume I took some time, it took me around 50 minutes to create a graph. So I'm not going to create it every single time. I just store it in my system and I'll fetch it back from there. So whenever I need it. So do you remember of any graph representations? What are the general ways of representing the graphs in memory? Can you throw some names at me in the chat window? No one? Some graph representation methods. Some of you might be teaching them in your discrete mathematics or graph theory course. It will help if you guys interact with me.
Yes, participants, are you there? This has been covered. I don't know why they are not responding. Chetan
Uh,
Suri, Gaurav Verma, Gurpreet Singh, Navita, Prince Madan, kindly respond in the chat window if you are there.
it's okay, it happens in the online classes. Okay, Gurpreet and Chetan replied. So can you please tell me about some of the graph representations we use? So how do you represent a graph mathematically? Yes, so one is the adjacency matrix. Okay. So adjacency matrix is like one of the most basic way in which we represent the graphs, but then we have many other kind of representations also. So what's wrong with adjacency matrix that we need all those other kinds of representations? Okay, incidence matrix, adjacency list. Why do we shift from adjacency matrix to adjacency list? Can someone tell us the reason? So we have an adjacency matrix kind of a representation. Why actually to shift to adjacency list, which is rather using some pointers because you store it as a linked list.
Ma'am, because in adjacency matrix we can't go beyond 2 degrees. Means if we have to represent more degree of number, then adjacency list will work better. That
A
will
more
reduce
degree of number means
means जैसे कि हम 3 by 3 matrices कर like 3 degree matrices
okay.
जैसे
Based on the dimension, you can only
dimensions.
represent
Yes, ma'am.
2 cross 2. So
Yes.
3 cross 3 will be different.
So
Okay.
adjacency list would be rather simpler to represent for more dimension points.
Okay. So for more dimensions, it might become complicated. But if we talk in terms of graph, so we just need 2 dimensions, right? So we are every row represents a vertex, every column represents a vertex, and aij equals to 1 if you have an edge between those two vertices. Any other disadvantage you face with adjacency matrix? Let's actually do that and look at that. What is the disadvantage if I use an adjacency matrix here? Uh, so we created this graph, small g here, which had some node attributes and stuff like that. So let's look at the first representation here, which is the adjacency matrix. So we know what it is. It's an n cross n matrix where n is the number of nodes, and you'll have a 0 at a place if there are no edges between those two nodes, 1 if they have an edge. So right now I'm conceiving an unweighted network, not a weighted one. I'm going to use this. So you have a direct function here, g dot get underscore adjacency to look at the adjacency matrix of a vertex. And here you can see a matrix of all zeros and ones. And you will see ones in all those places where you have an edge between the two nodes. Now, if you see here at this matrix, it has a very large number of zeros. So this is for the graph we created on our own. If you look at the real world networks, it's the same situation with them too. So all of them are sparse graphs as compared to, so if you have a graph on n nodes, there are actually order of n square edges possible and choose 2 edges possible, which is actually huge. And you have very less edges out of those actually in your graph. So most of the graphs are sparse and you have these large number of zeros which end up eating a lot of your space if you represent them in adjacency matrix representation. So one way, what we can do is, so one way to cut off this is if I'm looking at an undirected graph. So this one over here is a directed graph. So you can see that this matrix here is not symmetric. If it's an undirected graph, it will be a symmetric matrix. So in the case of an undirected graph, it's a symmetric matrix. So what you can do is actually cut down the upper triangular or the lower triangular part of it. So even in the case of I graph for adjacency matrices for undirected graph, you get a parameter here inside this get adjacency, which helps you check out the upper triangular or the lower triangular part. So cutting out your space requirement by half. But still there are a large number of zeros anyway. So that's why adjacency matrix representation is generally not used when you are working with very large graphs. So here we get an adjacency matrix for an undirected, for a directed graph here because it's not symmetric. Now let's add some weights to our original graph and then try to look at how we get the weighted adjacency matrix. So I'm going to add an attribute to every edge and that attribute is going to be named as weight. So till now we have added the attribute f name to each of the vertex. And now we are going to add an attribute weight to each of the edge. So the method is exactly the same. For the vertices, we use the vertex sequence. Similarly, for edges, we have the edge sequence object. So this shows me an edge sequence object. Let me see if I can list it and see what it stores. So you can see here 5 different edges which we were having in the network, and similar to the vertices, the edges are also indexed in an increasing order, so from 0 to 5. And these curly braces are actually for storing the attributes of these edges. So as of now, we don't have any attribute here. Let's go ahead and add some attributes here. Similar to the vertices, instead of GS, I just write an ES and followed by some edge weights. So I have 6 edges here. So let me simply add some 6 weights here. Okay, and again, if you look at this edge sequence object, you can see here that I have this attribute weight here now. You can also use it in the visualization of your graph. So when we did this IG dot plot G. So if I simply plot it, you see this graph. Assume that I also want to see the weights of my edges in this visualization. So I can use a parameter here. I want my edge width to be equal to, and I'll again have to provide a list here which has the weights of all these edges here. So you go ahead and do this, then you can see now your edges are having these different widths, and these different widths are dependent on what is their weight. Okay, we diverted a bit. So we were at the point where, so now this graph has become a weighted graph. And what we want to do is look at the adjacency list of this weighted graph. So the function remains the same, g dot get underscore adjacency. However, we have added an attribute weight now. So we need to provide it here. So if you simply execute g dot get underscore adjacency, it won't show you a weighted adjacency matrix. You need to provide a attribute weight here. If you do that, now you can see that every one is replaced by the corresponding weight of that particular edge. So this is how you display the adjacency matrix on the screen, but our objective is to store this graphing system. So better to write it in a file. So writing it to a file is also straightforward. So here we were using the function g dot get underscore adjacency. So you just remove this get, make it right. So it is g dot write underscore adjacency. It's going to write this adjacency matrix in a file now, but you need to provide the name of the file here in this F here. So I'm going to provide the name of a file here. Let's say AM for adjacency matrix, and just execute it. And then you can again go back to your system and you'll see this file AM here. You can open it and see it here. So this adjacency matrix here is stored in your system. And let's say you want to read back this adjacency matrix. So now I have stored it. I want to get it back, and I want to read it to a new graph here. So I'm going to read this am.csv in an altogether new graph here. So let me name it. Name is g underscore am. So this is a graph which is made from an adjacency matrix which was stored on my system. I'm going to use this graph class here, graph. There is a slight difference between the functions if you see. So maybe after this session, I'll share a PDF with you and the relevant resources. So if you look at these functions, there will be slight difference. For example, in read adjacency, you have both R and A in capitals. In write adjacency, you have those in lowercase, so on and so forth. You need to be careful about that. And then I'm going to pass here am.csv. Now this was my weighted graph. So I might be tempted to use here the same thing, attribute equals to weight, but you need not do that. So it says that the name graph is not defined. So I need to import this graph also. So I'm going to do here from iGraph, import graph. And now you can look at, let me look at the summary of this here. So you can see here that it's a directed graph. Hmm. Okay. So some problem with this one over here. So this adjacency matrix, it was my weighted matrix, but the graph which I get here, it is only directed. It's not weighted because if it was weighted, I would have seen a W here at the place of the third dash, as we discussed before. So in case you want it to be weighted, you actually need to use that here. Attribute equals to weighted. The temptation was actually right. Yeah. So if you do this, so now you see that it's a directed graph and weighted graph. However, it is not named and it is not bipartite. So this was the first representation, which is adjacency matrix. Then someone talked about this adjacency list representation. Hmm. So let's now look at the adjacency list representation. So we move to adjacency list because adjacency matrix eats up a whole lot of space. So again, the function is simple. You can use g underscore get g dot get underscore adj list to look at the adjacency list of this graph. So what it gives you is a list of lists. What this is, so this is the vertices which are adjacent to node 0. So nothing is adjacent to node 0. Vertices which are pointed by node 1, vertices which are pointed by node 2, so on and so forth. But how do you write it to a file? So that is a bit difficult, I would say, in iGraph. Not difficult, it's done in rather a different format. So if you have network X, in network X you have a read adjacency list function in which you can provide the data, which is something like this. If I'm giving it some data like this, it will simply mean that node 1 is adjacent to 2, 3, 4, 2 is adjacent to 4, 5, 3, and 3 is adjacent to 1, 2, 3. But it does not work in the same way in the case of iGraph. So iGraph has a different format for it, which is actually called the LGL formats. And one advantage of that format is it also stores the weights of your edges. So generally, if I'm talking about the adjacency list representation, so all of us know that every vertex in the graph is connected to a linked list, points to a linked list, and that linked list has the nodes which it is adjacent to. But how do you store the weights there? So you can store the weights by making in every linked list, instead of each node having just two parts, it can have three parts, and where each part can carry a weight. So you can do a similar thing here. So here in the case of iGraph, to store an adjacency list, we use this write underscore LGL followed by your file name. So I have an adjacency list here. If I simply do this, g underscore write underscore LTL this, it actually shows me an error. So whenever you run in these kind of errors, just refer to the documentation of these functions. So here the actual documentation of these functions says it has a number of attributes. So the first one is the file name. Second one goes like this, names equals to, and you have to give an attribute name here. So this corresponds to the vertex names. So if you do not have any vertex names, you actually have to provide a none here. And similarly, it has an attribute weights where you need to type what is the edge weight, which attribute you want to use as the edge weight. If you don't have any edge weight, use a none here. It has one more attribute which is called isolates. Isolates take care of, there are some isolated vertices in the graph, whether you want them in the adjacency list or not. So if you want, you can check them out of the adjacency list. So let's say for now, let me do an isolates equals to true. Let's say I also want these isolated vertices, and then let me write it down and just look at this file which is created here. So this format is slightly different. So what it is doing is #1 tells me that I'm looking for the adjacency list of the first node here, and it is adjacent to 8. So my node 0 is not adjacent to any node. It is not pointing to anything. So it comes here at the last. but it is still stored because I have done an isolate equals to true. So an isolated vertex also appears here, and then node 2, which vertices is it? It is adjacent to, similarly for node 3, 4, and 6. Now, I can do some changes here and see what I'm going to do now is in names, instead of none, let me use f name. And similarly in edge weights, instead of none, let me use weight, and then see the difference here. So what it has done is, instead of storing the nodes by their indices, it has stored them by their names. So you have hash Aman, hash Vishal, hash Aman. So Aman is adjacent to E, and your edge weight also appears here. So Aman points to E. There is an edge from Aman to E with a weight 5. There is an edge from Vishal to Aman with a weight 1, from Vishal to Solanki with a weight 2, so on and so forth. So this is how you use the adjacency list format here. And there is one more thing associated with it. So if your graph has multiple edges or loops, so this breaks down this LGL format. So this file doesn't support multiple edges or loops. So if you add a multiple edge in your graph or a loop, you will run into a problem. So most of the times, rather always, when you store a graph in this format, you should first simplify it. Make it a simple graph which has a multiplicity of 0 and multiplicity of 1 and no self loops. Similarly, you can read from the adjacency list. So for that, you have again a read underscore LGL function. So let's say I'm reading a graph from my adjacency list. Again, I need that graph here, graph dot read underscore LGL. And now the file I'm going to use is al.csv. Now this one again also has certain parameters. So first one is names. If you set this names equals to false, when it will import that data, you will just see the indices. If you set names equals to true, so what will happen is all those names which we were having in this file here, they will come back to your original graph. They will come back to this g underscore al, but this time they will be in the parameter name, not in the parameter f name. So that you need to take care that the name of the parameter changes, and then you can have weights, and I can actually just set its value equal to if present. So if they are present, you get those weights, and then you can set whether your graph is directed or not. And just look at the summary of this graph here. So here you see it's a directed graph, and now you see a N here. So this is a named graph, which means each of your vertex has a name. It's a weighted graph. It has 9 nodes. It has 6 edges, and the attribute for each vertex is now name. So that f name has now changed to name when you exported it and when you imported back. So the name of the attribute changed here. So this was another representation. Coming to our almost the last representation, which you find most of the times in real world networks, that is your edge list representation. So you simply list down all the edges in a graph. That's it. So edge list representation, it definitely doesn't care for your isolated vertices. It stores only the edges which are present in the graph. So assume that I want to see this edge list for our current graph. So it shows you the edge list. So we have used this one before. So these are the edges in my graph, and I can again write this edge list and I can read this edge list. Let's actually do this with a real world network and then see how it happens. So most of you might be aware of this Stanford dataset collection. So I'm going to take a graph from there. So we'll look at some more data sets with time. So it gives you all these kinds of networks. So you should choose a network depending on your need. If you, these are the social networks. So some of them will be undirected, some will be directed, some will be signed networks. So signed networks, they have a sign associated with each as positive or negative. So assume that I want to portray a network on a classroom with both the friendship ties and the enemyship ties. So I'm going to use a signed network. Then the networks can be temporal. So I'll have a snapshot of the network at different times. The network keeps changing. Temporal networks are better handled by NetworkX rather than iGraph. So if you're working with temporal networks, you can uh, go ahead with NetworkX, and then you can have some bipartite networks here. Here there are some networks in which they say that they have certain communities present, but then you should be careful here. So by communities, what they mean is they have just looked at the connected components of the graph. So when you look at the documentation, you can find that out. It's not that they have actually applied a community detection algorithm here and used it. I think those are the kind of graphs you get here. So some graphs have some metadata, which can be some node attributes, so on and so forth. I'm actually going to take this very fast network from here, which is a an induced subgraph on Facebook.
Yeah, Yati, and how we can visualize a bipartite graph?
Ma'am, I'll come there in the visualization part. But yeah, just for knowledge, if you want to visualize a bipartite graph, so what can you do is each of its vertex is given an attribute which is called type. So generally, when we visualize a bipartite graph, what we'll want is probably different types of nodes should have different colors. So one part should come in blue color, other should come in red color, or one should be circular and other should be having some other what I would say, some other shape. So you can allocate a type attribute there, and based on that, you can give some color to those vertices. And if you want to analyze a bipartite graph, we'll talk about that. You'll have to take its projection. So you'll have to project it to a unipartite graph and then look at it.
Okay, ma'am.
I'm going to take this file here, Facebook underscore combine.txt. So it has edges from all the egonets combined. So in the overall network, whatever are the edges it gives me. Have this network here. Where it is extracted. Let me just show you this file first. So this file looks something like this. So this is an edge list. It tells me that there is an edge from vertex 0 to 1, 0 to 2, so on and so forth. So it is in the perfect format. The vertex indices are starting from 0 here, right? Rather, but I do not know whether all these are consecutive indices or not, or whether some number is missing from the middle or not. So that I'm not sure. But anyhow, this is a file which I have in the proper edge list format. I'm just going to save it on my desktop and coming back here. I want to read it. I want to give it a path here. Okay, so it actually doesn't support the backslashes. So this you have to always take care of this lowercase and uppercase things. So here I have this graph. You see this here. So since so it may actually made a directed graph here. So that's my fault. So this Facebook graph is actually undirected. So while reading it, you should set this directed equals to false here. So by default, it all the functions they do create directed graphs only. So now it becomes an undirected graph having 4,039 nodes and around 88,000 edges. So in the next part, I'll show you how you can visualize this. So this one is a big graph here. If you visualize it in Network X, it will take quite a lot of time to come up and it might even slow down your system. Here also it takes some time, but not that much. So these are some commonly used graph representations. So the three most commonly used: adjacency matrix, adjacency list, and edge list. There are few more representations which I think you can explore on your own. They are not used that much. So one is the incidence matrix and other is the incidence list representation. So incidence matrix is, instead of having a n cross n matrix, you have an m cross m matrix where m is the number of edges and then you populate that matrix. So I'm not going into that part. So all these graph representations or the graph storage techniques which we have seen till now, they have a major drawback. Has any of you noticed what is the drawback? It's just an observation based question. So what do you think? So you have seen that what all we can store. So we can store which node is adjacent to which other node and maybe edge weights and sometimes the names of the vertices. Is there something we are unable to store in these representations? So what if your vertex, every vertex has 3 attributes? What if every edge has 10 attributes? How do you store them? So let's say my every vertex has F name and L name, age, gender, marks, institution, designation, and a whole lot of other things. How do you store that? So adjacency matrix, it doesn't store that at all. Adjacency list, it can store at most one feature. So in this case, we used F name. Edge list doesn't again store any of that. So that is one problem when we use any of these graph representations. We can neither store the more than one attribute for nodes nor for edges. And whenever we work with any real world data set, and let's say you have done a survey and collected a data on your own, you can have a very large number of attributes there. Before that, what happens sometimes? So we are going to talk about some very commonly used formats which are used when you have these vertex and edge attributes. But before that, one thing here is sometimes you have formats which are not exactly edge list, but they will look similar to the edge list. So they will have some one, they'll have some extra rows and some extra columns. So let me actually show that here. This was from an assignment from Texas University. So if you look at this data set here, so this is called a Dimax format. So if you look at it, it has some additional things here. So it has a P, SP, and then this 32768, 52, 4288, so on and so forth. So you see a lot of numbers here. And then in every row you see it is preceded by an A. So it is a format of its own kind. So P and SP are some special things. P refers to pointer, A refers to arc, and this 32768 here, this one is 32768. This one is the number of nodes. After that is the number of edges, and then so here you also have edge weights, right? So you have an edge from 1 to 166 followed by an edge weight, and edge from 1 to 389 followed by an edge weight. So what you can do is sometimes if you have the graph in this format, it is best to read this graph in a pandas data frame, and then you can check off this first row and this first column from here and then pass that data frame for a graph creation. So we'll talk about that soon. Before that, one thing I actually missed. So when we look at this edge list format, we have also looked at an edge list here. So again, one disadvantage of the edge list is this one here is not storing your edge weights. So you simply have an edge list. This node points to this node. This node points to this node, so on and so forth. So there is one more format which is used to store this edge list alongside the edge weights. So that is called an ncall format. So you can use this. So this one is for again our original graph which we created from the very beginning. So if you use this one here, this is the name of my file. And again, instead of those vertex indices, you can use an attribute here. So I'm going to use this f name, and you also need to give this parameter weights equal to weight. This is again a different kind of representation. And again, if I go back and look at this file here, so you can see now it is slightly different. So what it has f name, so which node points to which other nodes, followed by the edge weight. So I think this one you should use when you have those weighted networks in your data set, which has 3 columns. If you have 2 columns, you can go with edge list. You can even use this ncall with 2 columns also. And if you want to read it, then again you can read it with the help of this function here, read underscore. So again here this n is in capital. Your file names equals to true. Again your attributes will be imported, but they will come in an attribute named name, not in the attribute f name. And similar to the previous function on adjacency list, you can pass this weights equals to f if present. If you don't want weights, you can type a weight equals to none here, and whether you want this graph to be directed or not. And see that now again it's a directed graph, it's a named vertex, it's a weighted graph. So we'll be soon looking into this bipartite networks, as ma'am said, how to visualize them, how to make sense out of them, so on and so forth. And then it has 2 attributes, name for vertices and weight for edges. Again, this one also suffers from the same problem as before. So we cannot store more than one vertex attribute or more than one edge attribute here. So we'll now talk about few more formats which can do this. So let me see if I can show you all the formats at one place. Okay, not here. Maybe I'll search that file and show it to you. Yeah, so this one over here. So here you can see all these different formats which iGraph supports. So adjacency list. So this one is named as LGL here. So we have already looked into this. If you want to look more about LGL, so you can always look here. So it shows you what is the file format exactly. Then adjacency matrix, the Dimax, a directed list, edge list. So these formats till here, I think you cannot use them to store multiple vertex and multiple edge attributes. So we'll be talking about some of these formats here. So this GML, GraphML, and this pickle format here. And for a matter of fact, even this one here, the last second, .NET format. So they are used a whole lot when you look at the online data sets. So I think we have almost reached the time for the tea break. So I'll take it up from here in our next session so that we start at a specific point where we are talking about storing graphs with all the vertex and all the edge attributes.
Okay, Atiman. So participants, you can have a break now for next. We'll start at 11:30, ma'am.
We started a bit, okay, we'll start at 11:30. Yes, yes, sure.
You can tell, please. We can start early also. No props.
We can start at 11:30. That is fine. That's fine.
Okay, fine, fine. Okay, participants. See you at 11:30.